Hi, this is Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss problem solving on computer arithmetic, multiplication and division. Computer arithmetic, it refers to the methods and techniques that the computer can use to perform mathematical operations on numbers. So we are performing various arithmetic operations on the data which is stored in the registers of the computer. So here the pipelining is a technique of decomposing a sequential process into sub-operations with each sub-process being executed in a special dedicated segment that operates concurrently with all other segments. So here in a computer, a large task is divided into sub-operations, and each sub-operation is performed in a dedicated segment so that a larger task will be completed the task in a shorter span of time. So that by using this pipeline technique, we can increase the execution speed of the computer. So each segment performs partial processing dictated by the way the task is partitioned. The result obtained from the computation in each segment is transferred to the next segment in a pipeline. So here the task will be divided into sub-operations, and in each sub-operation it will be allocated to each segment. Okay, so finally by passing the data through all the segments, finally we are getting the result. So each segment, it consists of an input register followed by a combinational circuit. So here in this particular block diagram, mainly we have three segments. So each segment followed each segment having input register followed by a combinational logic circuit. So this multipliers, adder, multiplier, adder. So these are all the combinational logic circuits. So combinational logic circuit means this multiplier, adder, these are all designed using a basic logic gates. That's why they are called the combinational logic circuits. So here already we know register. What is register? So register is a group of flip-flops. So using the register, we can store some information. So these are the registers. This is R1 register, R2 register, R3 register, R4, R5. So these are all the registers. So using these registers, we can store some information. Then we can perform certain operations on that registers. So in order to operate, so a clock is applied to all the registers after enough time has lapsed to perform all segmented activity. So in order to work on all the registers, they should require some clock. So we should provide a clock in order to operate certain operations on that registers. And the information flows through the pipeline one step at a time. So the information that flows through the pipeline one step at a time. So here we can see step-by-step manner. Suppose if you consider an example, some expression is given AI into BI plus CI. So A suffix A suffix I into B suffix I plus C suffix I, where I is equal to 1 to 7. So we need to get the result of this expression. Okay. So the sub operations performed in each segment are, so total in this segment, in this block diagram, we have three segments. So in first segment, the values will be loaded into that particular register. So during the first segment, AI will be loaded into R1 register, BI value will be loaded into R2 register, because here where I is equal to 1 to 7, that means initially I will be 1. So that means A1 value will be loaded to R1, B1 value will be loaded to R2. After that, I is equal to 2. That means A2 will be loaded to R1. Similarly, B2 will be loaded to R2. So like that, go on I equal to 7. So by the time I is equal to 7, we will get the final result of that expression. So during segment 2, so multiplication operation will be takes place. So R1 multiply with R2, because here at when I is equal to 1, A1 will be loaded into R1, B1 loaded into R2. So that means R1 contains A1, R2 contains B1. So R1 multiply with R2. That means A1 multiplied with A2. So that result will be stored in R3 register. And during the segment 2, the CI means 1. CI means 1. 1 will be loaded into R4, and during segment 3, R3 plus R4. That means addition operation will be takes place, because the R3 contains multiplication of A1 A2, and R4 contains C1. Here addition operation will be takes place. R3 plus R4 contents will be added, and the result will be stored in the R5 register. So in this way, the data will be flows in a step-by-step manner, and by the time when I is equal to 7, we will get the final result of this expression. So here we can see step-by-step manner during each step. So here the clock pulse number. So during first clock pulse, A1, because initially I is equal to 1. I is equal to 1 means A1, B1 are the inputs. So A1 will be loaded to R1, B1 will be loaded to R2. Okay, so that is the operation during the first clock cycle. During second clock cycle, A2 will be loaded into R1, B2 will be loaded into R2, and A1 and B1 multiplied and that will be stored in R3, because when R1 R2 are multiplied, that result will be stored in the R3. When the multiplication result is transferred to R3, a new value, that is A2 B2, will be loaded into this R1 R2. Okay, and C1 will be loaded into R4. During third clock cycle, A3 will be loaded into R1, B3 will be loaded into R2, A2 into B2 will be loaded into R3, C2 will be loaded into R4, and A1 into B1 plus C1 will be stored into R5. So in this way, by the ninth clock cycle, we will get a A7 into B7 plus C7. So this is a final result of that expression. Okay, so in this way, the data will flow step by step, and finally, once the data is passing through all the segments, finally we are getting the result. So this is called pipelining. So any operation that can be decomposed into sequence of sub-operations of about the same complexity can be implemented by a pipeline processor. This technique is efficient. So this is efficient. That means it consumes less time. Efficiency is more. For those applications that need to repeat the same task many times with different sets of data. So this type of pipelining concept, especially we are using when we are performing repeated works, repeated tasks. That means finding the factorial of a number, like that. So For this repeated tasks, this pipeline concept is a efficient method. And a task is the total operation performed going through all the segments of a pipeline. The general structure of four-segment pipeline is as shown in figure. So this is a four-segment pipeline. Four-segment pipeline. So already we know every segment has input registers and followed by a combinational logic circuit. Suppose if you take this one segment one, it is having some input and it is given to the R1 register. Okay. Then R1 data will be given to the segment 2. Then it is given to register R2. Okay, once the data passing through the register, passing through the segment, the result will be stored in the register. So total we have, this is a first segment, second segment, third segment, fourth segment. So total we have 4 segments. And coming to the problem, illustrate the following arithmetic expression using 1, 2, and 3 address instructions. That means we need to implement the arithmetic expression x is equal to a plus b into c plus d using 1 address instruction, 2 address instruction, and 3 address instruction. So let's see using 1 address instruction. So 1 address instruction is also a format of machine instruction. It has only 2 fields. That means a single address instruction, it has only 2 fields. The first one is the opcode, second one is the operand. So single address instruction, it has only 2 fields. The first field is the opcode and the second field is the operand. So opcode means operation to be performed. So the opcode will decide what type of operation it has to be performed, whether it is a load operation, store operation, add operation, multiplication operation. So that is a opcode. So opcode means it decides what type of operation the processor has to be performed. That is a opcode. So examples of the opcode are load, add, mul, subtract. So these are all the various examples of the opcodes. And coming to the operand. Operand is nothing but on which we are performing the operation. Okay, that is the operand. Suppose if you performing addition operation, if you're performing addition, add b, this is one of the example of the address, one of the instruction. So add b, that means what type of operation we are performing, addition operation. So it is a opcode. What is this b? B is a operand. That means add b, that means the contents of b register is added with accumulator. So that means accumulator plus b. The contents of b register is added with the contents of the accumulator and the result automatically stored in the accumulator. Okay, so that's why operand means on which we are performing the operation. So here b is the operand. That means b, in the b register we have some data. On that data we are performing this addition operation. So this is using 1 address instruction. Okay, so let's see how this arithmetic expression will be implemented. So initially first we need the sum of a plus b. So first I am loading my a into register. So load a, that means the register a value will be loaded into the accumulator. A value will be loaded into accumulator. Then add b, add b. That means b value is added with accumulator, because in accumulator already a is there. So with that a, I'm adding this b. Okay. So now the accumulator contains a plus b. Okay. And after that, once I got the sum of a plus b, that I'm storing somewhere in the memory. So store temp1. So temp1 is it is a name of the memory location. Suppose if this temp1 will be 4000, that means my sum result, that means a plus b, it is it will be stored in the memory location 4000. Okay, so that means in 4000 I have my sum result. Later I want sum of c plus d. So I'm loading c to accumulator. So load c, that means in accumulator it has c, and then add d. That means the contents of d is added with the accumulator, because in accumulator already it has a c value. So now if you add, if you perform addition, it becomes c plus d. It becomes c plus d. Again, that sum of c plus d, I am storing somewhere in, I am multiplying. So mul temp1, because in temp1, what is the temp1? Temp1 is 4000. What is temp1? Temp1 is the name of the memory location. In that memory location, I have sum of a plus b. That sum of a plus b, I am multiplying with this accumulator. Multiplying with the accumulator, because in accumulator I have c plus d. Okay. Finally, once I got the result of this expression, I'm storing somewhere. I'm storing the final result in x location. So store x. So store the final result in x. Okay. So this is how the arithmetic expression can be implemented using a S1 address instruction. And coming to the to address instruction. These instructions specify two operands or addresses. So previously we used to specify only one operand, but here we can specify two operands because of this two address instructions, which may be memory locations or the registers, which may be the memory locations or registers. So the syntax will be add add a b c. Okay, add a comma b, add a comma b. So here this is a source, this is a destination. Okay, so here these two operands, they could be both can be registers, or one can be memory location and other can be register, but both should not be a memory locations. For example, a to address instruction might add the contents of two registers together and store the result in one of the register. This is common in commercial computers. Here, two addresses can be specified in instruction. Unlike earlier in one address instruction, the result was stored in accumulator. Here, the result can be stored at different locations rather than just accumulator. So previously, in one address instruction, when you perform any operation, the result automatically stored in the accumulator. But here, that is not mandatory to store the result in accumulator. Instead of accumulator, we can also store the result in some other registers, like here add a comma b. So that means when you perform addition of this a and b, the result will be stored in the register a. But if I want to store somewhere register, I can use it. So like add c comma b. That means I am adding the contents of register b with register c. That means here the result is not stored in accumulator. That means I have modified the destination register. Okay, so here using this two address instruction, not mandatory to store the result in the accumulator itself. We can store any register instead of the accumulator. So the given expression is x is equal to a plus b into c plus d. So this we are going to implement using two address instruction. So the format of the two address instruction format will be opcode, and the destination are source 1 and source 2. Okay, so opcode, destination are source 1 and source 2. Okay, so already we know what is opcode. Opcode is it tells what type of operation the processor has to be performed, and this is a destination also. So this operander, it acts as both the destination field as well as the source field, and this is a operand 2. So see here. So in order to get the sum of a plus b, first I am loading a into one register, move r1 comma a. So r1 will a will be stored in r1. Next add r1 comma b, because in already r1 I have a. In r1 register the value a is there. So this a I am adding with this r1. So I got sum of a plus b. So where it is there? In r1 register. So in r1 register I have sum of a plus b. Next move, I am taking another register, that is r2, and I am loading the c value into that register. So c to r2. Next add r2 comma d. So d value I am adding with the r2 register, because in r2 register already I have c. So now c plus d, that means sum of c plus d is available in r2. So in r2 I have c plus d. Okay, so I have sum of a plus b and I have sum of c plus d. Now I need to perform multiplication. So I am performing multiplication between the r1 register and r2 register. So mul r1 comma r2. Okay, so in r2 I have sum of c plus d. In r1 I have sum of a plus b. Now both gets be multiplied, and result will be stored in the r1, because r1 is a destination register. So move x comma r1. So from the register r1 I am copying the data or result to the x location. So this is how we can implement using the two address instruction. And coming to the using three address instruction. So in the one address we have only one operand. In two address instruction we have two operands, and in the three address instruction we have three operand fields. So computers using three address instruction format can use each address field to indicate the register of your processor or the operand in memory. The assembly language program which evaluates the formula as follows: x is equal to a plus b into c plus d, and is accompanied by notes describing each instruction's register transfer process. So the format of the three address instruction like this. The first field is a opcode field. So in any instruction, the first field will be opcode only. So first field is a opcode, and the second one is a destination field. Third one is a source one, and fourth source two. So two source operands and one destination operand is there. Okay. So I need sum of a plus b. So add r1 comma a plus b. So that means this is source 1, source 2. I am adding this to a plus b, and after performing addition the result will be stored into r1. That means now the r1 contains the sum of a plus b. Similarly add r2 c comma d. So d is added with c, and the result will be available at R2. Okay, so now R1 have sum of A plus B, R2 have sum of C plus D. Now I am multiplying this R1 register with R2. So mul x comma R1 comma R2. So multiplication. After multiplication, the result will be stored in X. Okay. So this is how we can implement a arithmetic expression using one instruction, two address instruction, and three address instruction. And the slides are prepared by referring the textbook M. Morris Mano, Computer Systems Architecture, Pearson, 3rd edition, 2015. And the other textbook, John D. Carpinelli, Computer Systems Organization and Architecture, Pearson, 1st edition, 2001. So in this lecture, we have seen computer arithmetic multiplication and division, and we have seen the how the pipeline process will be executed, and also we have seen how the computer arithmetic expression will be implemented using one address, two address, and three address instructions. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.